This is 8.7. We're solving problems with exponential and logarithmic functions. Same idea as yesterday. We're just working more so with word problems today. So our goal is to pose and solve problems based on applications of exponential and logarithmic functions. So the first example, we're given a chart, and this is data that represents data from 1997, a computer store. So the demand of computers versus the price of computers. So we get this table of values here, where as we can see, as the price of the computer comes down, the demand of the computer goes up. Okay? This investigate is not very good. I've gone through it in the book. It's not very helpful. So we're not gonna spend too much time on this. We're gonna focus more on the actual problems in this section. If we look at the questions, it says, based on the table, what do you predict the demand would have been for the computers priced at $1,600? So this is similar to what we've done in the past. We've looked at kind of the data points that are between or close to 1600 on either side, and then we look at the demand and we take kind of the median or the middle between them. All right, so we can guess here that the demand would be somewhere in the neighborhood of 168. B, it says, create a scatter plot. So if we were to do a scatter plot, it looks something like this. Okay, but really the reason why the investigate, this is our price here, and this is our demand. But the data, you know, it's inconclusive. There's just not enough data points to really determine whether it's a linear representation, a quadratic representation, or an exponential. So for that reason, the investigate's not very good. It's not very clear. So they end up using a graphing calculator using the regression function. Anybody familiar or not familiar with the regression function? Basically, you put in a table of values into the graphing calculator and you press a button and it gives you a formula for that. Okay, so there's various formulas that could be created. One is a linear, one's a quadratic, one's a cubic. Okay, it says use the regression feature on a calculator to determine the equation of the curve of best fit. So those, let's see what they look like. So here's the regression formulas down here. So these formulas were developed again just by putting those values in a table of value and pressing a button, and they give you the different formula types. So then we can use those formula types to make estimates about the data. Okay, E says which type of function gives you the best fit, and they determine that based on the data. It's difficult to say, but they say that the linear function is maybe the best fit. It says use the algebra model you found to determine the price that would have a demand of 195 computers. So all they would do then is take this algebra or the formulas that have been developed on the calculator, and they put in 125 for the demand, and then they calculate the price. Okay? And they can do that for the various different models, the quadratic or the linear models. So again, not an extremely useful investigate. It's just showing you more or less that you can take any data set, a table of values, and create different models, whether they be linear or quadratic models. Let's focus on the examples. So the first one, it gives us an example of pH. Okay, so in chemistry, the pH is the measure of acidity or alkalinity of a substance. It's based on a logarithmic scale, so you might have seen this in chemistry. A logarithmic scale uses powers of 10 to compare numbers that vary greatly in size. So for example, very small and very large concentrations of the hydrogen ion in a solution influence its classification as either a base or an acid. So we can see here, as the concentration of hydrogen ions increases, so we have more hydrogen, the solution becomes more acidic. Okay, and the pH goes down. All right, so very high concentration of hydrogen ions, we have a very low pH and a very acidic solution. Okay, so we can see the varying substances in those different pHs. So pH 0 is battery acid, pH 1 is hydrochloric acid. That's in our stomach, that's used to help break down food. pH 2 is lemon juice, and so forth. Okay, the most basic solution we can come up with would be liquid drain cleaner. All right, bleaches and oven cleaner are also very basic. So the difference of 1 pH unit represents a 10-fold times change in the concentration of hydrogen ions. So this is similar to the Richter scale that we looked at yesterday. So there's this kind of logarithmic relationship between the numbers and the actual what's happening in actuality. So we can see here, for example, the acidity of a sample of pH 5 is 10 times greater than the acidity of a sample with pH 6. Okay, so as these numbers get increasingly lower, get increasingly greater, the concentration of hydrogen ions is either increasing or decreasing at a much greater rate. Okay, so let's get to the question. It says the relationship between pH and hydrogen ion concentration is given by this formula. So here's our formula, one that we should be pretty comfortable with understanding and using at this point, all from the practice yesterday, where H is the concentration of hydrogen ions in moles per liter. First question says calculate the pH if the concentration of hydrogen ions is 0.0001. So we would just take this concentration of hydrogen ions and sub it in here and solve for pH. Okay, so we would just take the negative log of 0.0001. All right, so that's A here. So we take that 0.001, sub it into the formula, we take the log, it ends up being -4 because that's the value that 10 needs to be the exponent of to get that value. It's -4, so our pH becomes 4. Okay, and that correlates with our chart here of pH is equal to 4. All right, B, if the pH of lemon juice is 2, calculate the hydrogen ion concentration. So again, we're going to take this value of 2 now for the pH, and we're going to sub it in for pH. So we do that in B here. We sub in 2 for pH, and that's equal to negative log hydrogen concentration. So now we need to solve for the unknown, which is H. So we can rearrange this equation in exponential form. So log H is 10 to the exponent of -2 is equal to H. So we solve for H. Any questions there? So again, there's not much new from yesterday. We're just taking word problems and now applying the logarithmic laws that we've learned to solve for the unknown. Finally, the last part, it says if the hydrogen ion concentration is a measure of the strength of an acid, how much stronger is an acid with pH 1.6 than an acid with pH 2.5? So we take each one of those values, pH 1.6, and we're going to solve for how strong it is. And then we take 2.5 and we're going to solve for how strong it is. And then to find out how much stronger one thing is than another, we divide them, right? You take the value of one, divide it by the other, and that'll tell you how much stronger or more powerful that particular solution is. So we sub in 1.6 for our pH. We solve for our hydrogen concentration. We do the same thing with 2.5. These are separate equations. We solve for that hydrogen concentration, and then we divide them to find out that the first scenario is 7.84 times stronger. Any questions about that? It's the only thing that's maybe been added new in this section is just determining how much stronger something is than something else. You need to divide them, right? All right, and you'll see that again with this example, I believe. So example 2, we're going back to the Richter scale here. It's the magnitude scale that uses logarithms to compare the intensity of earthquakes. So here's our true intensity, and here's our Richter scale. So 10 to the exponent of 1, we get a Richter scale magnitude of 1. 10 to the exponent of 4, we get a Richter scale magnitude of 4. So an earthquake of magnitude 2 is actually 10 times more intense than an earthquake of magnitude 1. Again, that's because we're on a logarithmic scale. The difference between the magnitudes of two earthquakes can be determined the difference in intensity. If the average earthquakes measure 4.5 on a Richter scale, how much more intense is an earthquake that measures 8? Okay, so the two values we're given is 4.5 and 8. So we want to measure both of those intensities and then divide them to compare. So if it's 4.5, the actual value then would be 4.5, 10 to the exponent of 4.5. So to find out how much stronger one is than the other, you just divide them. Okay, and when we divide exponents, we can subtract them, and we find out that it's actually 3,162 times more powerful. Okay, so that's a lot, right? Very, very big difference between 4.5 and 8 on the Richter scale. All right, number 3. This one is the rate at which blue jeans fade. Blue jeans fade when washed due to the loss of blue dye from the fabric. If each washing removes about 2.2% of the original dye from the fabric, how many washings are required to give a pair of jeans a well-worn look? For a well-worn look, jeans should contain at most 30% of the original dye. So we need to know to get from 100%, decreasing each wash 2.2% to get to 30%. Okay, so the first thing we do is we develop an equation. Each time the jeans are washed, you're going to take that new value of dye and subtract 2.2%. So we take that 2.2%, we convert it to decimal. Okay? And all of this is to the exponent of the number of times that it's washed, n. So we develop this formula here. So the dye percentage is equal to 0.978 to the exponent of the number of times it's washed. We substitute in the value. Yep.
How'd you get 0.978?
1 minus 0.022.
And where'd you get the 1 from?
The 1 is starting with 100% of the dye, and the 2.2 is the amount you're going to lose each time you wash it. Okay? So it's similar to a financial problem in that regard, right? Your initial amount minus the percentage you're losing. So then we substitute in values. We want to get to 30% of the dye left, so that becomes 0.3. And we want to solve for n, so we just use the logarithmic laws, the power law, to lower the n from the exponent in front of the log term, and then divide the log terms to solve for n. Any questions there? So this, arguably the most difficult part would have been setting up that equation. Okay? It's important to realize that you can't just subtract 2.2 from the original 100 so many times, right, to get to 30. Does anybody know why we can't do that? Why can't we just take, if the jeans are going to fade at 2.2%, why not just take the original dye of 100% and keep subtracting 2.2 and then count how many times you wash it to get to 30%? Why can't we do that? No, it's not why. That's not why. It's actually, you did get the wrong answer. Why, Alan?
Because every time you subtract, the 2% is less each time.
Yeah, exactly. Okay, do you guys understand that? Yeah. Because once you wash the jeans the first time, right? Now it's not at 100% anymore. It's at 97.8%. Okay, so you can't just subtract 2.2 from 98.7. You have to go back to 100%. Therefore, this equation is necessary. Right? You have to keep subtracting 2.2 from the new faded jeans, right? Because the second time you wash it, they're not going to fade 2.2% from the original condition. They're going to fade 2.2% from the new condition, or the new faded value. Does that make sense? You guys understand that? That's why we can't just take a linear scale and subtract 2.2, 2.2, 2.2. Wouldn't take very long, right? To do that, if that's all we're doing. It's a logarithmic scale. So the percentage of dye is decreasing at a slower rate. Yeah.
So why can't we go from 100 minus 2.2 and then 97.8 minus 2.2, then the next value minus 2.2 next?
Because each time that you wash the jeans, there's a different amount of dye in them that you need to subtract the 2.2% from. You can't just keep taking off 2.2 from the original 100%.
Yeah, no, it's not the original one, the new one. Like, why don't you just do that?
Okay, I'll try to explain it one more time. So, if we take off 2.2% from the 97.8, right? So the second time you wash it, right? You're taking more than 2.2% off now, because there's not 100% of the dye in those jeans the second time you wash it. There's less dye.
Oh, yeah.
So you have to take 2.2% of the 97.8%. You guys get that?
Yeah.
That's why. Okay? So that's why this formula is required. Okay? It's not a linear scale, but that die is reducing. So by taking a percentage of that reduced die, it's a logarithmic scale. Okay? All right. So we end up with 54 washings to give the jeans a well-worn look. If we did a linear scale, how many washings would it be? Let's just do this in our head very quickly. So if we had 2.2, 2.2 times x is equal to 70, right? Because we want to reduce the 100 by 70. So x would be 70 divided by 2.2. So we're looking at somewhere in the neighborhood of 30-ish. What is that? 70 divided by 2.2? Nobody has a calculator?
31.8.
Okay. 31.81. So, see the difference? We had to actually wash it 54 times, not 31 times. Okay? Alright. Number 4. The dynamic range of hearing and sound intensity spans from 10 to the exponent of negative 12 to about 10. The highest sound intensity that can be heard is 10 trillion times as loud as the quietest. This span of sound intensity is impractical for normal use. A more convenient way to express loudness is a relative logarithmic scale, with the lowest sound that can be heard by the human ear. The initial intensity, remember naught stands for initial, is equal 10 to the negative 12, given the measure of loudness of 0 dB. So you guys are probably familiar, you've probably seen this unit before, right? When measuring sound, decibels, yeah. Recall that the formula that is used to measure sound is L is equal to 10 log intensity over the initial intensity, where L is the loudness measured in decibels, I is the intensity of the sound being measured, and I naught is the intensity of sound at the threshold of hearing. The following table shows the loudness of a selection of sound measured in decibels. Alright, so here we have a table of values measuring everything from a soft whisper to a space shuttle launch. And this is measured in dB. How many times more intense is the sound of a rock concert, so we're looking at this one, than the sound of a subway? Okay? So if we were working on a linear scale, we would just take this divided by this, and that would be our intensity, right? 1.3 or whatever it is. Okay? But we're not. Okay? We've already just been explained in that log paragraph that we're using a logarithmic scale. Logarithmic scale is given to us by this equation. This was given in the problem here. L is equal to 10 log I over I naught. So all we do then is we take those decibel values and we plug it into those scales. And at the end, what are we going to do with our two values at the end to find out how much more something is than another, or how many times more? What do we do with those two values, David? Yeah, we're going to divide them. So again, that's the only kind of new component, other than, you know, rearranging the formulas and using the logarithmic laws that we've learned today, is just to find out how much stronger is something than the other. You divide them. So if we take that 120 and we plug it in for L, okay, we end up with this solution here, okay? And we have two unknowns. The reason why that's okay is because when we divide, those unknowns, or the initial I naughts, are going to be canceled. Okay, so we do the same thing with 90. We take this value and plug it in here. Two separate equations. So we end up with these two values. The intensity of the rock concert and the intensity of the soft whisper. And then, as David told us, we're just going to divide those two values and the initial intensities cross out, and we find our value of 1,000. Just hold on, okay? I'm almost done. Any questions about this one? So the only trick with this one is that there was an initial intensity variable that we didn't know the value for. It was okay because at the end we were asked for a ratio, so we canceled them out. Okay? But again, the same idea. You're taking a value and you're substituting it in for the unknown variable, and then at the end, you're dividing them. Okay, the only trick again maybe might be for going from there to there. We need to realize that this is 10 to the exponent of 12 is equal to this value. That's how we get to there. All right, summary. When a range of values can vary greatly, using a logarithmic scale with powers of 10 makes comparisons between large and small values more manageable. Growth and decay situations can be modeled by exponential functions of the form f at x equals a bx. Note that f at x is the final amount, a is the initial, and for exponential growth, 1 plus the growth rate, and for decay, 1 minus the decay rate, and x is the number of growth or decay periods. This is also works for financial. Remember, that's the same equation where we have the new, or the a, the amount or the value is equal to p, the principal, times the base or the interest rate, so 1 minus if you're going down or 1 plus if you're going up, times the number of compounding periods would be the exponent. So it's also financial math problems as well. So we need to know scales that measure a wide range of values such as a pH, Richter scale, and decibel scale are logarithmic scales. To compare concentrations on the pH scale, intensity, and the Richter scale or sound intensities determine the quotient between the values being compared. So in other words, divide. And I always put the greater value on the numerator.